Hello everyone, welcome to my channel AURORABYTE. Today we are going to discuss the hyperconjugation. Hyperconjugation. This is called no bond resonance. It is also called sigma bond resonance because it occurs through sigma bond. It is also called Baker-Nathan effect. Baker-Nathan effect. So, what is hyperconjugation? To explain this, we consider a carbocation like this. CH, here is the carbocation, and here also CH3. Now, this carbon, it is sp2 hybridized. That means here is a empty p orbital is there. Empty p. Now to neutralize this compound, this carbon hydrogen bonded electrons shifts here and we get CH3 CH double bond C H and H. This phenomenon is basically called hyperconjugation. Here now this hydrogen which this carbon hydrogen bond which shifts here, so which carbon participates in the hyperconjugation? This carbon is called alpha carbon. So what is alpha carbon? The carbon directly attached to the carbocation. This is called alpha carbon. And what is alpha hydrogen? The hydrogen attached to that alpha carbon is called alpha hydrogen, and this alpha hydrogen shifts and make the hyperconjugating structures. So we can say that the number of hyperconjugation is proportional to, not proportional to, it's equal to number of alpha hydrogen. This point is to be noted. Now, through this hyperconjugation, we can discuss the stability. The stability is proportional to number of hyperconjugating structure. Now, let us consider an example. This is a carbocation. So, what is the number of hyperconjugating structure? Now, if we consider this structure, we have to find the alpha carbon first. So the directly attached carbon is this. So is this the alpha carbon? Answer is no. This carbon is sp2 hybridized. This is not a alpha carbon. This is not a alpha carbon. Alpha carbon, it's alpha carbon. Alpha carbon must be sp3 hybridized. This is very important. Now, if we consider this CH2C plus minus. So, number of hyperconjugating structure is what? Now, consider the alpha carbon. This carbon is sp3. So, it is the alpha carbon. And in this carbon, two hydrogens are attached. So, number of alpha hydrogen equal to 2. That means number of hyperconjugation structures is also 2. I'm sorry. Number of hyperconjugating structure is also 2. Now these are the examples of positive hyperconjugation. These above examples are of positive hyperconjugation. Positive hyperconjugation. Now if we consider the negative hyperconjugation, let us consider an example. Here is a benzene ring, carbon, chlorine, chlorine, chlorine. Now this carbon have the sigma star orbital, and this double bond shifts here and the chlorine leaves. We get here is a double bond carbon CH. Now this is the example. This is the example of minus H, that means negative hyperconjugation. Here pi to sigma star transition occurs. Pi to sigma star transition. Now what are the applications of this hyperconjugation? Now we will discuss the applications. Firstly, stability of carbocation. Stability of carbocation. We can define or compare the stability of carbocation through hyperconjugation. For example, this is a carbocation 3 degree, this is 2 degree carbocation, and this is 1 degree carbocation. Now, here the number of hyperconjugation structure is, these 3 are the alpha carbons. So 3 and 3 hydrogens are there, 3 into 3, that means 9 hyperconjugating structure is present. For this is 2 alpha carbons, that means 6 alpha hydrogens, and for this 1 alpha carbon, that means 3 alpha hydrogens are present. So the number of, not number, actually order, you can say the order order of hyperconjugation is A greater than B greater than C, and the stability is also A greater than B greater than C. So we can say the stability of carbocation is proportional to number of alpha hydrogen or number of hyperconjugating structures. This is very important point. Now the second application is stability of radical, stability of free radical. Stability of radical. This is very similar to the carbocation, similar to the carbocation. So we can write the stability of radical is also proportional to number of alpha hydrogen. We can write this. Now thirdly, stability of alkene. We can also describe the stability of alkene using hyperconjugation. Let us consider some alkenes like this, this and this. A, B, C, D. If we want to compare the stability order of these four alkenes, we have to count the hyperconjugation structures. Now for this number of alpha carbon, 1, 2, 3 and 4. 4 alpha carbon, and each carbon have 3 hydrogen, that means 12 alpha hydrogens. Here 3 alpha carbons are present, that means 9 hyperconjugating structure. Here 2 alpha carbons are present, that means hyperconjugating structure is 6. And here 2 alpha carbon are present, that means 6 alpha hydrogen, that means hyperconjugating structure is 6. So now order of hyperconjugating structure is A greater than B. In C and D, the number of hyperconjugating structure is same, C equal to D. But we can see here the C structure, it is a trans structure, and this is a cis configuration. We know the stability order is trans is greater than cis due to steric hindrance actually. Here two methyl groups are in same site, that means its repulsion occurs. So the stability order is A greater than B greater than C. It is trans structure, and greater than D. It is cis structure, it is less stable. Now the next application is heat of hydrogenation. We consider heat of hydrogenation. Heat of hydrogenation. What is heat of hydrogenation? It's basically heat released during During addition of hydrogen. Heat released during addition of hydrogen is called heat of hydrogenation. It is an exothermic process because heat released exothermic process. That means the enthalpy change is negative. Now let us consider alkene and add hydrogen. So we get alkene hydrogen addition examples. And the delta H is minus X. Let us X. This quantity is negative. Now, if we consider another end like this, double bonds are present. So we need 2 mole of hydrogen and we get this alkene. Here the delta H is minus 2x. The enthalpy change is doubled. So we can see the number of pi bond is directly related to the heat of hydrogenation. It's right that heat of hydrogenation is proportional to the number of pi bonds. Number of pi bonds, that means more heat released during hydrogenation. This heat of hydrogenation is also related to the stability of alkene. Heat of hydrogenation is inversely proportional to the stability of alkene. More stable alkene releases lower heat during hydrogenation. This point is very important. Now let us see an example. Alkene and this is an alkene. Order of heat of hydrogenation. What is the order of heat of hydrogenation? A and B. Now for this, firstly, we have to consider the stability here. We are going to use this relation. So to find the stability of alkene, we need to count the number of hyperconjugation. Here, 1 and 2 alpha carbons are present, and each carbon has 3 alpha hydrogen. So total 6 alpha hydrogens are present. That means hyperconjugating structures are 6. And for this structure, only 1 alpha carbon is present. That means 3 alpha hydrogens are present. So number of hyperconjugating structure is 3. So we can say the stability order is A greater than B. That means the heat of hydrogenation order is the opposite. Heat of hydrogenation order is B greater than A. In this way, we can compare the order of heat of hydrogenation from the stability and from the hyperconjugation. Some more applications are there. We will discuss them in the next class. So that is it for today. Thank you for watching. And if you like this video, so hit the like button. And if you have any doubt, please drop in the comment section. And if you are new to my channel, please subscribe my channel. See you in the next class. Thank you.